Hi, this is Jean-Francois with you today to discuss the integration by trigonometric substitutions. Trig subs are techniques that we use for two different cases, and we will examine in this video case number 1, those that involve a squared minus x squared forms. A trig substitution is a method that we would use if the integral is not basic, if simpler methods such as substitution or integration by parts fail, or if algebraic methods fail as well. Then what we're looking for are integrals whose integrands contain either a squared minus x squared or a squared plus x squared forms. In case 1, where we examine a squared minus x squared forms, we're going to use the substitution x equals a sine theta, hence the name trigonometric substitution. This is unusual because in the past we had chosen u subs to replace bigger portions of functions, whereas here we are going to take a simple expression x and turn it into something somewhat more elaborate. If x is a sine theta, then dx will be obtained by differentiating the right-hand side of x, so a cos theta d theta. Here we have to assume that theta remains between minus pi over 2 and pi over 2 for domain purposes when we return to the original variable x. Along the way, we will have to recognize that the substitution will lead to the use of sine squared plus cos squared theta equals 1. Actually, notice how using an x value of a sine theta and squaring it creates a common a square to both terms involved, and by factoring it, 1 minus sine squared theta can be recognized as cos squared. What we hope for is that this will result in something easier to solve. As for going back to x's, remember that if x is a sine theta acts as our substitution, then that would be equivalent to saying that sine theta is x over a, or that theta is arcsine of x over a. In either scenario, you can imagine a triangle whose angle theta must create a sine that has x over a as its ratio. Recall that a sine function involves the opposite and the hypotenuse sides, whose ratio by choosing x and a will be x over a. The third side is no longer up to us and is the result of Pythagoras. We will usually draw this triangle to ensure we can go back to x's by connecting theta and x in most of our steps. Here's an example. We are going to integrate 1 over 9 minus x squared. No matter what method you will try, none of them will succeed. Actually, a substitution fails since there is no 2x involved at the numerator to go along with dx. This is not a case of integration by parts, and splitting the denominator is not allowed. Completing the square doesn't seem to fit. 9 minus x squared is of the form a squared minus x squared. Therefore, if we think of a as being 3, this may appear like an expression we can apply a substitution of the trigonometric type. Let x equal a sine theta becomes x equal 3 sine theta. The corresponding dx, 3 cos theta d theta. Applying this substitution to our integral looks as if we are complicating it at first. However, remember that trig identities most likely will simplify some of the expressions. Squaring 3 sine theta generates a common 9 that can be factored from the denominator. And 1 minus sine squared now appears as something that can be replaced by cos squared theta. 3 and 9 were simplified to 1/3 and pulled out from the integral. Now finally observe how cos of theta and 1 over cos squared can be reduced to 1 over cos, which is, in fact, a secant. Now in case 6, or in the special cases of trig powers, we viewed the integral of secant theta d theta as a new basic antiderivative, whose outcome is ln of secant theta plus tan theta. An arbitrary k is inserted to have all possible antiderivatives. But wait, we started off with x's. Now remember, when we said that x was going to be equal to 3 sine theta, this also means sine theta is x over 3. And therefore, a triangle that illustrates this ratio of sides would have x as an opposite side, 3 as the hypotenuse, and the remaining side would be the root of a squared minus x squared. So, if our previous result said that secant theta was part of our antiderivative, then the hypotenuse over the adjacent reveals that secant theta can be expressed in terms of x. Our antiderivative also contained a tan theta term, which is the ratio of the opposite over the adjacent sides, also expressible in terms of x's. And therefore, our antiderivative can be converted back to x's. Because of the common denominator, we could also group these as one single term. If you are dealing with a definite integral, as usual, you may also adapt the bounds along the way. For instance, here's a scenario that involves an a squared minus x squared form. A substitution would fail, so would integration by parts or any algebraic method, and 4 minus x squared fits the forms we are describing here in case 1. So, let's associate 4 minus x squared to a squared minus x squared and let a be 2. If we apply the substitution, x equals 2 sine theta, then dx will have to be 2 cos theta d theta. There's no need to draw a triangle that will help us back to x's because this time we will adapt the bounds. Our lower bound was 1 as a value for x, but x is also 2 sine theta. So, sine of theta must be a half to correspond to the lower bound. And that would mean theta is pi over 6, as we're choosing angles between minus pi over 2 and pi over 2 only. The upper bound for x was root of 3, but must also fit with our choice of 2 sine theta. Hence, sine theta must be root 3 over 2, and the angle between minus pi over 2 and pi over 2 that fits the ratio root 3 over 2 is pi over 3. And we're set. We have new values for x and for dx, and we have new values for the bounds of x, 1, and root of 3. Here is what our integral looks like after applying our substitutions and our changes of bounds. If you expand 2 sine theta squared, a common 4 will appear. Factoring the 4 and replacing 1 minus sine squared reveals a cos squared expression in the term that is to the power 3 halves. Now, the power 3 halves, be careful, applies to both the 4 and to the cos squared. 4 to the power 3 halves is actually 8, and cos squared to the power 3 halves is cos cubed. Constants 2 and 1/8 can be factored out, and the common cosines can be reduced. Thankfully, 1 over cos squared happens to be secant squared, for which we have a direct antiderivative. No need to go back to x's as we have adapted the bounds, And our final step would be to simply input pi over 3 and pi over 6 and find the outcome of this definite integral. Well, we survived again.